Hey everyone, I'm JJ. What's up, guys? Welcome back to another episode of our radiographic physics series. Today, we're going to talk about one of those topics that many people totally mix up, the filament and the focal spot. Now you might be thinking, wait, aren't both of them just parts of the X-ray tube? Well, yes, but not exactly. Each one has a very specific role, and both directly affect your image quality. Alright, let's get straight to the point. So what exactly is a filament? The filament is basically a very thin wire made of tungsten. When an electric current passes through it, it heats up and starts releasing electrons, a process known as thermionic emission. The filament is located on the cathode side of the X-ray tube. Now here's something interesting. Almost every diagnostic X-ray tube, like the ones made by Varian or Varex, has two filaments, a small filament and a large filament. But here's the key, only one of them works at a time. The small filament uses less current, around 3 to 4 amps, which equals roughly 300–400 milliamps of tube current, while the large filament needs more, around 6.5 amps. Or up to 600 milliamps. Remember, that filament current, 3 to 4 amps, is just for heating the filament itself. It's not the same as the tube current. Once the filament gets hot enough to release electrons, those electrons create a tube current that can reach up to 200 to 300 millimeters for the small focus and around 600 millimeters for the large focus. So what does this mean? It means that when the small filament is active, fewer electrons are produced, so the focal spot will be smaller. When the large filament is active, more electrons are produced, and the focal spot becomes larger. In short, small filament equals small focal spot. Large filament equals large focal spot. Now here's a super common misunderstanding. When you select small focus or large focus on the generator console, you're not directly changing the focal spot. What you're actually doing is telling the generator which filament to heat up. So, when you pick small focus, you're heating the small filament, which sends a narrower electron beam toward the anode. When you pick large focus, you're heating the large filament, which sends a wider electron beam. And that's the real physical difference between the two. Alright, now let's move on to the focal spot. Alright, now that we know what the filament is and what it does, let's see what exactly the focal spot is. The focal spot is the point on the anode surface where the accelerated electrons hit, and that's where the X-rays are actually produced. So the filament is the source of the electrons, and the focal spot is the impact zone where the X-rays are born. Every X-ray tube typically has two focal spots, a small one, around 0.6 millimeters, and a large one, around 1.2 millimeters. Interestingly, these two focal spots are very close to each other on the anode surface, but they're not exactly overlapping. Each one hits the anode at a slightly different path, because the electron beam angles are a bit different. Now let's look at the side view, where the electrons hit the anode. If you take a look at the diagram on your screen, it shows a very important detail. On the left side, labeled cathode, you can see the two filaments, one small filament and one large filament. And on the right side, we've got the anode, which is tilted at about 13 degrees. Now let's see what happens more closely. The small filament, at roughly a 10-degree angle, sends a narrower electron beam toward the anode surface. The larger filament, at about 14 degrees, sends a wider electron beam instead. When these two beams hit the angled anode surface, we get two distinct impact areas, a smaller one, shown in cyan or teal, and a larger one, shown in red. That teal-colored region is where the electrons from the small filament strike. That's our small focal spot. And that red region, which is bigger, comes from the large filament. That's the large focal spot. Both of these are what we call actual focal spots. the real physical areas where the electrons hit the anode and X-rays are generated. If you look at the top right diagram, you can see a schematic of the anode showing exactly where the large focal spot and small focal spot are located, and even the focal track where the anode rotates. But here's the most important part. What we see from outside, from the detector's point of view, isn't these actual impact areas. Because of the anode's angle, what we see is a compressed projection of those spots, a smaller version of them. That's what we call the effective focal spot. So what does that mean? From above, the impact area is physically large, but because of the anode angle, it looks like a thin, narrow strip. And that's what makes the final image appear sharper and more detailed. Alright guys, now let's move on to the next part. This one's all about the line focus principle. If you followed everything so far, you already know that the anode in an X-ray tube is angled. But here's the question. Why is it angled at all? Why not just make it flat? Well, the reason's actually super simple. If the anode were completely flat, the area where the electrons hit would be tiny. Sure, that would give you high image sharpness, but there's a big problem. All that heat would concentrate in one small spot, and the anode would literally burn up. So engineers came up with a clever trick. They tilted the anode, usually at an angle between 12 and 15 degrees. That way, the actual impact area, or the actual focal spot, becomes larger, which helps spread out the heat across a bigger surface. But from the detector's point of view, because of that angle, the area appears smaller. So you get the best of both worlds, sharper images and a cooler, safer anode. That's what we call the line focus principle. Now there's a simple formula you can remember. Sine of the anode angle X. Actual focal spot equals effective focal spot. In other words, the effective focal spot equals the actual 1 multiplied by the sine of the anode angle. Let's do a quick example. Say your actual focal spot is 3 millimeters and your anode angle is 12 degrees. The sine of 12 degrees is roughly 0.2. So 3x 0.2 equals 0.6 millimeters. That means a 3 millimeters impact zone appears as just 0.6 millimeters. From the detector's perspective, that's exactly what makes the final image sharper and cleaner while also keeping the tube safe from overheating. Now, take a look at the image on the right. You'll see two diagrams there. On the left, the actual focal spot, the real impact area, on the anode surface. And on the right, the effective focal spot, how that same area looks from the detector's point of view. Notice how the one on the right looks smaller and more compressed? That's exactly why the image appears sharper and more detailed. And finally, a quick note about the table at the bottom. In that table, we're comparing the actual and effective focal spots. The actual focal spot lies on the anode surface, usually between 3 and 6 millimeters, and it's mainly important for heat calculations. The effective focal spot, on the other hand, is what the detector actually sees, typically between 0.6 and 1.2 millimeters, and it directly affects the image sharpness. Then here's the golden takeaway. If the anode angle increases, the sine of the also increases, so the effective focal spot appears larger. That means the image edges become a bit softer and the fine details lose some sharpness, what we call a soft image. But if the anode angle decreases, the sine value gets smaller, so the effective focal spot becomes smaller too. The edges look super sharp and crisp, but the heat becomes more concentrated. That's why in practice, engineers usually keep the anode angle between 12 and 15 degrees. It's the perfect balance between sharp detail and heat-tolerant scales. All right, now, let's talk about something really practical and important. You've probably noticed on the X-ray tube housing, it usually says something like 0.612 millimeters, right? So here's the question, what exactly do these numbers mean? Well, these numbers represent the effective focal spot sizes, not the actual ones. In other words, they're the sizes as seen from the detector's perspective, and they're what directly affect image sharpness. But if you look inside the technical data sheet, you'll often see another number listed. That's the actual focal spot, the real physical area. On the anode surface, it's usually a few millimeters larger because, as we explained earlier, it's compressed by the anode angle to create the smaller effective focal spot. To summarize, the number written on the tube equals effective focal spot. The number in the datasheet equals actual focal spot. Now, to give you a sense of scale, in most diagnostic X-ray tubes, we typically have small focal spot about 0.6 millimeters, large focal spot about 1.2 millimeters, and if you want to estimate the actual size, you can simply divide the effective size by the sine of the anode angle. For example, if the anode angle is 12 degrees, its sine is roughly 0.2. So actual equals effective 0.2. That means the 0.6 millimeters. Effective spot corresponds to about 3 millimeters. Actual and the 1.2 millimeters, one corresponds to about 6 millimeters. Actual. Now, in the figure or table we showed earlier, we compared these two focal spots side by side, but let me just highlight the key points. The actual focal spot is the real impact area on the anode surface where the heat accumulates. It's important for thermal calculations. The effective focal spot is what the detector actually sees, and that's what determines image resolution and sharpness. Typically, the actual size ranges from 3 to 6 millimeters, while the effective size is about 0.6 to 1.2 millimeters. And here's the main takeaway. The number you see on the tube is always the effective focal spot value. Okay, now let's talk about one of the most common questions students ask. When you select small focus or large focus on the X-ray generator, what's actually happening? Is the generator changing the size of the focal spot? Nope, the generator itself doesn't modify the focal spot size. It only decides which filament gets heated. So here's what happens. When you choose small focus, you're basically telling the system to heat the small filament. That small filament produces a narrower electron beam which strikes a smaller area on the anode, and that's your small focal spot. On the other hand, when you select large focus, the larger filament is heated, creating a wider electron beam which hits a larger area, the large focal spot. Now, let's talk about limitations, since the small focal spot concentrates heat in a smaller area. It can't handle very high tube currents. Typically, you can use up to about 200-300 milliamps safely. But the large focal spot can handle much more, up to around 600 milliamps, because the heat spreads across a larger surface area. So here's the rule of thumb. For fine detail images like hands, skulls, or small bones, use small focus for maximum sharpness. For thicker body parts, like pelvis or abdomen, go with large focus to prevent tube damage and allow faster exposure. Small focus equals higher sharpness, lower heat capacity. Large focus equals lower sharpness, higher heat capacity. All right, now that we know what a focal spot is and how it's made, let's talk about a very important topic, How focal spot size affects image sharpness. The bigger the focal spot, the electrons are emitted from a larger area and the X-rays hit the object from slightly different angles. The result? The edges of the image get a bit blurred. This is called geometric unsharpness. Here's a simple way to understand it. Imagine you're taking an X-ray of a hand. If the focal spot is very small, almost all rays come from a single point and the edges appear sharp. If the focal spot is larger, rays come from different points and each ray slightly shifts the edge of the object. Result: edges look a bit wider. This effect is most noticeable at the edges and in high detail images like hands or skulls. It's very obvious. The formula for geometric unsharpness is very simple. We call it U sub G. The letter U stands for unsharpness and G stands for geometric. The formula is U sub G equals F times OID divided by FOD. Here's what each part means. F is the focal spot size. OID means object to image distance. And FOD means focal spot to object distance. Let's look at an example. If the focal spot size F is 1.2 millimeters, the object to image distance OID is 10 centimeters, and the focal spot to object distance FOD is 100 centimeters, then we calculate U sub G equals 1.2 times 10 divided by 100. That gives us 0.1.2 times 10 divided by 100. That gives us 0.12 millimeters. Now if we use a smaller focal spot, say 0.6 millimeters, we get U sub G equals 0.6 times 10 divided by 100. That gives 0.06 millimeters. So the unsharpness becomes half of what it was before. Using a smaller focal spot gives you a sharper image. Key takeaways: smaller focal spot equals less geometric unsharpness equals sharper image. Smaller OID equals object closer to detector equals less blur. Larger equals object keep farther from object equals less blur. These three factors determine how sharp or soft the image looks. Important point: when the focal spot is large, only the edges blur slightly. The whole image isn't blurry. That's why we call it soft, not blurred. Tables summarize this nicely. Smaller focal spot equals sharper. Larger focal spot equals soft edges. Larger FOD equals sharper. Smaller FOD equals less sharp. Smaller OID equals sharper. Smaller OID equals more edge blur. So the rule of thumb: small focal spot plus far tube plus object close equals sharpest image. Examples for body parts: hand or wrist equals small focus equals high detail, noticeable unsharpness. Skull or knee equals medium focus equals moderate detail, medium blur. Abdomen or pelvis equals large focus equals low detail needed. Unsharpness, negligible. Alright guys, let's move on to another topic that often gets mixed up with focal spots: magnification. First of all, when we say magnification, we're not talking about zooming like on a phone. Here, it means because X-rays diverge from the focal spot, the object appears slightly larger on the detector than its actual size. The size of magnification depends on two distances. First, SID, which means source to image distance. That's the distance from the X-ray tube to the detector. Second, SOD, which means source to object distance. That's the distance from the X-ray tube to the object. The formula is magnification equals SID divided by SOD. Let's look at an example. If SID is 100 centimeters and SOD is 90 centimeters, then we calculate 100 divided by 90 equals 1.11. So the image will appear about 11% larger than the real object. How to reduce magnification? Move the object closer to the detector, reduce OID, or move the tube farther from the object increase SID. Important. High magnification can also make the image slightly less sharp because rays hit the object at more divergent angles. So as we discussed with sharpness, keep the object close to the detector. Remember, magnification depends on distances, not focal spot size, but focal spot affects how sharp that magnified image looks. Two images may be the same size, but the one with a smaller focal spot will be sharper. Choosing focal spot based on body part. Now let's make this practical. When to use small versus large focal spot. 3 main factors. Object thickness. Level of detail needed. Tube heat capacity. Examples: thin and delicate parts. Hand, wrist, teeth. Small focal spot. Low current, 50-100 milliamps. Tube heat is not an issue. High sharpness. Medium thickness. Skull, knee, chest need a medium or large focal spot. Moderate current, 200-300 milliamps. Need short exposure equals balance sharpness and heat. Thick parts, abdomen, pelvis, spine need a large focal spot. High exposure required equals distribute heat. Slightly less sharp, tube protected. And now summary: thicker objects equals larger focal spot equals control heat. Delicate, detailed objects equals smaller focal spot equals maximize sharpness. Final summary and key takeaways. Alright guys, let's wrap everything up real quick so it all sticks in your mind. Filament. It's the source of electrons. There are 2 types, small and large. We know small filament is lower current, around 300 milliampere. That means fewer electrons. Large filament is higher current, around 600 milliampere. That means more electrons. Focal spot is the area on the anode where electrons hit and X-rays are produced. When the small filament is active, means small focal spot. When the large filament is active, mean large focal spot. Actual versus effective focal spot. Actual, the real area, where electrons strike the anode. Effective, what's seen by the detector, appears smaller due to the anode angle. Alright guys, that's it for today's lesson. I really hope you enjoyed this session and found it helpful. If you liked the video, please share it with your friends, and don't forget to subscribe and leave a like. If you got any questions or something wasn't clear, just drop it down in the comments. I'll make sure to reply. It was awesome being with you again, and I'll see you in the next video. Take care, and goodbye.